Hello and welcome back to my organic chemistry channel. So today we're going to be looking over a bunch of extra little reactions you guys should probably know for the exam, and I'm just going to throw these in there. So we're going to start with CO2 chemistry. What is CO2? Well, it's carbon dioxide and it looks like this. This is its Lewis structure. Now, how do we actually use this for organic chemistry? Well, I'm about to show you. Most likely you're going to see problems that look like this, where it's reacting with a Grignard reagent. And how this works is you will get something that looks like this when you react a Grignard reagent with CO2. Now, if we actually look at this in real time, that's supposed to be a carbon. We actually get this resonating in, and then the Grignard coming in to attack, leaving us with this final product. So I hope you can see how that works real time. So let me draw it out. We're starting with CO2 and reacting with the Grignard reagent. We resonate this up to either oxygen, opening up this orbital, which then, just like a regular Grignard reaction, can come in and attack, giving us our product. Now then, if it is then present with acid workup, H3O plus or H plus, we can then tack on a hydrogen to our negatively charged oxygen, giving us this product for CO2 with acid workup. But I hope you see how that works. Not too hard to grasp this. Looking at the final product, or the final question, let's see how this one works real quick. Let me move it down here. So all I want you to do is ignore all this stuff. The only thing we really care about is the Mg and the CO2. So once again, carbon, 2 double bonds to oxygen, resonate one up, making this oxygen negatively charged, making this carbon positively charged. So now then our Mg can come in and attack, giving us our overall product. That looks like this, because once again, we don't care what that actually is. It's not reacting with the CO2. We just have to redraw it in. The only thing that's actually reacting with the CO2 is the carbon attached to the Grignard. And then since we are, once again, reacting this with H3O plus, add on a hydrogen to the oxygen, like that. And that's how CO2 chemistry works. So moving on to saponification. Saponification is pretty simple. The easiest way to think of this is, I like to think of it as deprotonation of the carbon chain, leaving the oxygen with a negative charge if you see an AOH. But the actual mechanism of it and how it actually works is NaOH is an ionic compound. So Na is going to be positively charged, OH is going to be negatively charged. When we have an alkene aldehyde or something like that, we can actually resonate the bond up. The nucleophile can come in and attack, giving us this intermediate right here. We can then break this bond, resonate this down, giving us this plus this. And these would be your two products. Now, the one you'd actually probably care about, in this instance, I doubt I'd give you something like this, but these are technically both organic compounds, so you probably have to draw them both out. That's for esters. For this one, what would happen is same thing. You're going to be left with the negatively charged oxygen attached to the ketone. And then you would have EtOH. Next one, draw out your compound. Negative charge on the oxygen plus isopropanol. And that's saponification. Anytime you see NaOH, that's what happens. OH acts as a nucleophile because NaOH is a ionic compound. And I showed you the mechanism, so that one's pretty self-explanatory now. Hope you can grasp that. Moving on to the next reaction, the Fischer reaction, or as I like to call it, the Charmander reaction. It's basically the same as an acetyl formation reaction. However, it can also deprotonate carboxylic acids and actually add on the prefix of the alcohol being used in the reaction. And how this works is, if you see this emblem, that then means that there is heat involved in this reaction. And that's the difference between the acetyl formation and the Fischer reaction, because it utilizes heat in order to break those bonds. It does also follow the same rules as the acetyl formation, so I'll show you what I mean by that in this first example. As you can see, we're reacting this with H plus and MEOH, so you would actually be given something that looks like this, and that would be your final product. Once again, the Fischer reaction reacts at the carboxylic acid, replacing the carboxylic acid with the prefix of the alcohol. So we replace the hydrogen with the prefix of the alcohol right here, gets replaced with right here, and then it just does a normal acetyl formation at the ketones and aldehydes, but the carboxylic acid ketone is unaffected, so don't touch that, just leave it as its normal carboxylic ketone. So the next one, how would this work? Same thing occurs here. H2O reacts, H plus touch H2O. We will then add, this will be eliminated, and you would be left with a regular carboxylic acid. Once again, we have another carboxylic acid reacting with EtOH and H+. Easiest way to remember these is replace the hydrogen with the prefix of the alcohol. And once again, these only occur with that heat. That's the difference between these and the acetyl formations. So I hope that helped. I'm going to make a couple more videos probably on acid chlorides and stuff like that, and then we'll just go over some practice problems and you guys should be set. Have a wonderful day.